In the previous part, we have learned that sending a spin current into a ferromagnet can lead to a spin transfer torque on the magnetic order. In this part, we are going to inspect how the magnetic order reacts to such a torque. We will see that the torque can trigger either auto-oscillations or magnetization reversal. We will see that one can also excite thermal spin waves and possibly Bose-Einstein condensates. Finally, I'll say a few words about potential applications.
To understand how spin torque can manipulate the magnetization, we consider a magnetic spin valve and we inject a current from the pin layer in blue into the free layer in red. The magnetization of the pin layer is called P and that of the free layer is called M. Let me draw a frame XYZ where Z is perpendicular to the plane of the free layer. Because the free layer is extended along X and Y and is relatively thin along Z, there's a sizable demagnetization along Z. In addition, we also consider that there is a uniaxial anisotropy along the X-axis. So Z is a hard axis and X is the easy axis. Okay, so the magnetization dynamics is described by the LIG equation, which consists in three terms. The first one is the precession term, and HF is the effective field that contains both the external field, the uniaxial anisotropy, and the demagnetizing field. The second term is the magnetic damping, and the third term is the spin transfer torque. Here the polarization is taken along the x-axis parallel to the easy axis. I will manipulate this equation to find what the stability conditions are. I want to know what critical field and currents are needed to induce magnetization switching. To do that, I will consider a small perturbation around the rest position of the magnetization. I start with the magnetization aligned along the easy axis and I'll tilt it away from it so that the My and Mz components are very small. I obtain these coupled equations. I can solve them by assuming that the magnetization makes small oscillations around the easy axis at a frequency omega. Now we will be particularly interested in the imaginary part of the frequency. If this imaginary part is negative, the state is stable as the deviation vanishes exponentially as a function of time. On the contrary, if the imaginary part is positive, the deviation diverges and the state becomes unstable. So I inject the ansatz into the coupled equations above and I solve the determinant. This gives me the eigenfrequencies of the system. You see that it has both a real part and an imaginary part. As I just said, I'm only interested in the imaginary part because it gives me a criterion for stability. I therefore obtain a critical current at which the magnetization switches, depending on its initial direction along X or along -X. With the critical current at hand, we can build the stability phase diagram of the free magnetic layer. In this graph, I report the magnetic state as a function of the external field and as a function of the torque magnitude. Let's first look at the field. When the external field exceeds the anisotropy field, the only stable configuration is when the magnetization of the free layer is parallel to the polarizer. Conversely, when the field exceeds -hk, the magnetization must be anti-parallel. In between these two boundaries, both parallel and anti-parallel states are stable. Now I draw the boundaries determined by the critical current. Again, on the right side, the only stable configuration is the parallel one, whereas on the left side, I get the anti-parallel configuration. So in summary, in the yellow region, the parallel state is stable, while in the red region, the anti-parallel state is stable. In the middle of the diagram, the yellow and red regions overlap, resulting in a bistable magnetic phase. Now, there is something we haven't considered yet. Is the importance of thermal fluctuations. As we have seen in a previous lecture, the thermal fluctuations are particularly important in small magnetic volumes, and they limit the lifetime of a given magnetic state. When a spin-polarized current is present, the dwell time of the magnetic state is severely reduced, as demonstrated experimentally. The consequence of thermal activation is the smoothing of the boundaries in the magnetic stability diagram. The bistable region looks more like a potato than a square, as confirmed experimentally.
How does magnetization switching occurs under spin transfer torques? Let me show you a couple of simulations using the Landau-Lifshitz-Gilbert equation for that same uniaxial magnet we just discussed. When destabilized by the spin torque, the magnetization starts precessing circularly around the easy axis. The cone angle increases progressively, and when the magnetization reaches the plane perpendicular to the easy axis, it switches and relaxes toward the opposite direction, still precessing around the easy axis. If I add the demagnetizing field, the precession becomes elliptical because the magnetization must now also precess around the hard axis. Nonetheless, the overall dynamics is not qualitatively modified. In reality, the magnetization of the free layer is not a macrospin, but rather a large collection of magnetic moments better represented by the macromagnetic assumption. Therefore, the magnetization switching occurs more likely via the nucleation and propagation of magnetic domains, such as the ones shown in the picture. Hence, the switching occurs via different states of excitations displaying large magnetic fluctuations during the reversal process.
Spin transfer torque is a fantastic tool to control the magnetization of small magnets with a current. It has been investigated in a lot of different materials and different configurations in order to reduce the critical current required for magnetization reversal. What have we learned over the years? The torque efficiency is given here, as we have seen previously, and the critical switching current is given by this formula. Let's scrutinize this expression. First, you see that the critical switching current is proportional to the thickness of the ferromagnet. The thicker the ferromagnet, the more current you need to switch its magnetization. Therefore, you should look for a material that can be as thin as possible. The problem is that most magnetic materials tend to lose their saturation magnetization upon reducing the thickness. In fact, some magnetic materials even display a dead layer below 1 nanometer. In addition, the magnetic damping also tends to increase upon size reduction. Intense research has demonstrated that the best compromise is to use transition metals with a large magnetic moment, such as cobalt iron boron, that retains a sizable magnetization down to 0.5 nanometers. Second, we need a material with a strong spin polarization. As we have seen in the previous lecture, the best system to date is the iron MgO magnetic tunnel junction that displays more than 99% spin polarization for delta 1 electrons. Another approach, which can be combined with MgO tunnel junctions, is to engineer the spin dephasing in the ferromagnet by adding a capping layer. For instance, you have here the hysteresis loop obtained by Zheng et al. On a magnetic spin valve when the free layer is capped by a thin ruthenium film. You see that the critical current can be massively reduced just by adding this capping layer. To understand that, you can consider the picture right below. If the free layer is very thin, the spin dephasing is not strong enough and the spin current that is injected from the polarizer is not entirely absorbed by the free layer. Some of the spin goes through the free layer without being absorbed, which creates an opposite torque on the outer interface of this free layer. If you add a capping layer like ruthenium, this layer acts as a strong spin scatterer that destroys the outgoing spin current, and therefore, the switching current is severely reduced. Okay, let's move on. To reduce the critical current, you can also choose a material with a small saturation magnetization and a small damping. Of course, the saturation magnetization cannot be reduced arbitrarily, otherwise your free layer enters the superparamagnetic limit. But there's room for improvement and several types of materials have been investigated. For instance, gallium manganese arsenide possesses a very small saturation magnetization, which results in critical currents down to 10^5 amp per centimeter square, one order of magnitude smaller than what you obtain with transition metals. The problem is that the Curie temperature is also quite small, around 160 K. So to date, the best compromise is obtained for cobalt iron boron, with an MS of 800 mu per cc and a Curie temperature far above room temperature, even down to 1 nanometer. Finally, you can also work on the magnetic anisotropy and demagnetizing fields. You cannot really get rid of the magnetic anisotropy because you need it to retain the magnetic information. However, you can work on the demagnetization and try to reduce it. The solution that has been proposed is to use perpendicularly magnetized spin valves. In this case, the demagnetizing field is aligned with the anisotropy field, and by engineering the interfacial anisotropy, one can substantially reduce the critical current. This is good, but as I said, you still need some decent anisotropy energy to prevent thermal fluctuations and maintain the magnetic information. An alternative idea put forward by Bernard Jenny at Spintech was to heat the free layer locally using a current pulse to facilitate magnetization reversal. This thermally assisted technique allows for switching magnetic layers that possess a large magnetic anisotropy. I conclude this discussion by presenting what is currently the standard system used for spin torque switching. It consists of a magnetic tungsten junction composed of thin cobalt iron boron magnetic electrodes separated by an MgO barrier. These junctions are shaped as tiny pillars of a diameter of 100 nanometers and below, down to 20 nanometers or so, and the critical switching current is typically around 10⁶ ampere per centimeter squared in the best cases. I would like to take a few minutes to talk about an interesting issue one can find in magnetic tungsten junctions. As I mentioned previously, you have two main types of spin torque, the damping-like and the feed-like components. In a magnetic tungsten junction, the damping-like component is mostly proportional to the bias voltage across the junction, with a small correction at the second order. In contrast, in a symmetric tungsten junction, the feed-like torque is purely quadratic in voltage. It can acquire a linear component when the structural symmetry is broken, for instance if you use two different magnetic electrodes. This behavior has been confirmed experimentally by Suzuki's group in Osaka and Dan Ralph's group at Cornell. An interesting feature is that the two torques, damping-like and feed-like, are opposite for negative bias and have the same sign for positive bias. In other words, they cooperate and compete with each other depending on the bias voltage. When they cooperate, the magnetization direction is stable, but when they compete, they trigger large magnetic fluctuations that are called backhopping, because the magnetization hops back and forth between parallel and anti-parallel configuration. To solve this issue, one can engineer the structural symmetry breaking, as done in this work led by Kyunjin Lee at KAIST. Depending on the composition of the magnetic electrode, one can tune the structural asymmetry and thereby the linear coefficient of the feed-like torque. If this coefficient is positive, there's a large region in the magnetic phase diagram where both parallel and anti-parallel states are unstable. However, if you tune the structural asymmetry in such a way that the coefficient becomes negative, then you can expand the stability region for parallel configuration and get rid of the backhopping issue. To conclude this presentation of current-driven switching, let's look at the magnetic phase diagram obtained experimentally in a copper-cobalt spin valve. This experiment was performed by the group of Dan Ralph and Bob Berman at Cornell, who pioneered most of the experimental research in spin transfer torque. On the right, you have the resistance of the device as a function of the external field and applied current. The blue region refers to parallel states, while the orange region refers to anti-parallel state. So we recover the diagram that we discussed at the beginning of the lecture. I would like to attract your attention on the greenish region here. In this region, the magnetization is neither parallel nor anti-parallel. In fact, the resistance is just intermediate. To understand what is happening here, you can look at the left diagram. This one reports the power of the resistance fluctuations recorded in the microwave range. In the voltage configuration, the fluctuations are small, which makes sense because the system is stable. In the anti-parallel configuration, the fluctuations are still rather low, although a bit larger due to Magnon emission that is present in this regime. But most importantly, in the region of intermediate resistance, the fluctuations are quite large and can be in fact very large. So spin transfer torque can induce large magnetic fluctuations. Let's look into it. Spin wave emission induced by spin transfer torque was originally proposed by Luc Berger in his pioneering work of 1996. Consider a spin valve in anti-parallel configuration. In the previous lecture, we have seen that injecting a current from the left to the right electrode results in a spin accumulation in the central layer. This accumulation creates an excess of down electrons at the interface with the right magnetic electrode. Because there's more down electrons than up electrons, the chemical potential of the down electrons is larger. These down electrons can relax their energy by flipping their spin and emitting a magnon in the ferromagnet. This is the mechanism of current-driven spin wave emission. At the interface between the spacer and the ferromagnet, one can define an Ohm's law that connects the interfacial spin current with the magnon density and electron spin accumulation. One can derive this expression using Fermi's Gunner rule as done by Zhang and Bender. The interfacial spin current is proportional to the square of the SD exchange and involves both magnon emission and magnon absorption, while ensuring the energy conservation. Now is probably a good time for a crash course on magnons. Magnons are elementary magnetic excitations. If you consider a spin chain, a magnon corresponds to the flip of one magnetic moment. Because flipping one spin costs a lot of exchange energy, the spin chain prefers to accommodate a delocalized collective excitation. This collective excitation is called a magnon. Because it corresponds to a spin flip, the magnon has a spin of minus h bar, so it's a boson and it carries a quantum of energy. From a mathematical standpoint, a magnon is obtained by considering the Heisenberg exchange of a spin chain. In its ground state, each spin is aligned along Z, and introducing magnetic excitations is achieved by allowing the spin to deviate from its rest position by a small quantity. This small deviation is then quantized using Erskine-Primakov transformation and introducing creation and annihilation operators A dagger and A, respectively. By doing that, you can demonstrate that the Heisenberg Hamiltonian reduces to a harmonic oscillator. Now, to model the interaction between magnons and electrons, we use the so-called SD exchange interaction, which we have already seen in previous lectures. I apply again the Erskine-Primakov transform, and I obtain the electron-magnon interaction Hamiltonian that pretty much looks like the more familiar electron-phonon interaction. The first term stands for the magnon emission, whereas the second term stands for the magnon absorption. Let's come back to our balayer. As I mentioned previously, if I manage to accumulate spins against the ferromagnetic interface, spin flip results in magnon emission in the ferromagnet. In other words, I can derive a boundary condition that connects the spin accumulation with the magnon spin current. The quantity that connects them is called the spin convertance, because I convert a spin current carried by electrons into a spin current carried by magnons. I also have the reciprocal effect. Imagine I find a way to accumulate magnons on the ferromagnetic site. These magnons pump an electronic spin current, and I can define another boundary condition that connects the magnon chemical potential with the electronic spin current. For the sake of completeness, I give here the spin convertance that you can obtain by working out Fermi's Gunner rule. You see that it involves the electron density of states, the magnon density of states, and the energy derivative of the statistical magnon distribution. If you want to learn more about the electron-magnon spin conversion at magnetic interfaces, I encourage you to have a look at Adachi and Bender's works. They give important theoretical insights about the interaction of electron-mediated and magnon-mediated spin currents. I'd like to wrap up this discussion by looking at the various situations you can obtain depending on the external control parameters of the system. First, what are those external parameters? The most obvious one is the electronic spin accumulation that you can create by injecting a spin current on the metallic side. The second parameter is the difference between the temperature of the ferromagnet and the temperature of the normal metal. This temperature difference creates an imbalance in the spin accumulation on each side of the interface and thereby modulates the interfacial spin current. Now let's look at the nature of the magnetic spin current that one can excite in the ferromagnet. Remember that magnons are bosons, so they are subject to Bose-Einstein condensation. In other words, if you tune the external parameters wisely, you should be able to force all the magnons to collapse to the ground state. Therefore, the magnons present in the ferromagnets are in a general superposition of both condensed magnons and thermal magnons. One can derive a continuity equation for the magnons where the rate of change of the magnon number is compensated by the dissipation of the condensate, the torque on the condensed magnons, the dissipation of the thermal magnons, and the torque on the thermal magnons. The dissipation of the condensed magnons is proportional to the magnetic damping, whereas the torque is proportional to the spin convertance and driven by the difference between the magnon energy and the electron spin chemical potential. Both currents are proportional to the number of condensed magnons. The expression of the dissipation and torque experienced by the thermal magnons is a bit more involved. These currents are still proportional to the damping and to the spin convertance. But in addition, the dissipation and torque are governed by the difference of temperature between the thermal magnons and the phonons on the one hand, and between the thermal magnons and the electrons on the other hand. The Magnon continuity equation has been derived and studied by Bender and Salkovniak. What they discovered is that by tuning the temperature difference across the interface and the electron spin accumulation at the interface, very different regimes can be obtained. As long as the electron spin accumulation remains below a critical threshold, the system is in the linear regime. When the temperature difference and the electron spin accumulation have the same sign, they cooperate to excite thermal magnons, and no condensate is observed. When they have an opposite sign, the temperature difference is such that it removes thermal magnons from the system, so that Bose-Einstein condensation of magnons dominate. Finally, by increasing the spin accumulation beyond the critical threshold, the system enters nonlinear coherent magnon emission, called the swaying effect. Swaying is equivalent to lasing. It is the spin wave amplification by the stimulated emission of radiation that was proposed by Berger in 1996. To the best of my knowledge, thermally induced Bose-Einstein condensation of magnons has not been observed yet. However, magnons have been injected thermally and detected in non-local magnetic spin valves. I present here the experiment performed in Bart van Wijs' group in Groningen. They used an yttrium iron garnet magnetic insulator on which they deposited 2 platinum leads. By injecting a current along the left lead, they create spin accumulation at the interface with the magnetic insulator. The spin accumulation comes from the spin Hall effect, an effect that will be discussed in details in a future lecture. This spin accumulation excites thermal magnons that propagate in all directions in the insulator. Some of these magnons reach the right platinum electrode and generate a new spin accumulation. Via the inverse spin Hall effect, this spin accumulation induces a potential drop along the platinum electrode, which signals the presence of non-equilibrium magnons. Using this apparatus, the authors were able to inject and detect thermal magnons, and by changing the distance between the 2 platinum leads, they were able to determine the length over which the magnon spin current propagates. They obtained that the typical magnon spin relaxation length is about 10 microns in YIG, which is 1 order of magnitude larger than electron spin relaxation length in copper. A similar work has been recently achieved by the group of Matthias Klaue in Mainz, but this time considering an insulating antiferromagnet. Again, they obtain a very large magnon spin relaxation length that far exceeds the electronic spin relaxation length in light metals. These experiments tell you that magnons are excellent information carriers, in fact much better than electrons, as they can propagate over distances exceeding 10 microns. We have seen how spin transfer torque can excite magnons. Now I want to better understand the nonlinear regime where swaying occurs. To do so, I come back to Kiselev's phase diagram and to my microspeed model. The two approaches, nonlinear coherent spin wave emission and macrospin auto oscillations, refer to the same physics. Of course, representing the excitations by nonlinear spin waves is closer to what happens for real and gives a much richer behavior. So let me remind you the system we're looking at. We have a tri-layer with a polarizer P aligned along the uniaxial anisotropy axis. When the magnetization is excited, it experiences a torque from the applied field, the uniaxial anisotropy field, and the demagnetizing field, so that it precesses around the anisotropy axis following an elliptical path. On top of that, it also experiences the magnetic damping and the spin transfer torque. The simplest model I can use to describe the magnetization dynamics is the macrospin Landau-Lichess-Gilbert equation that we have seen in a previous lecture. When I solve it for the tri-layer described in the previous slide, I obtain this magnetic phase diagram as a function of the external field and applied current. At large positive current and negative field, we have the parallel states, and at large negative current and positive field, we get the anti-parallel state. In the center, you recognize the bistable region where both parallel and anti-parallel configurations are stable. Now I want to look at the top right-hand corner, where funny stuff happens. In this region, the field and the torque compete with each other. The field wants to pin the magnetization in the anti-parallel configuration, whereas the current wants to pin it in the parallel configuration. As a result, the magnetization direction varies rapidly. Let us fix the external field and look at the trajectory of the magnetization for different currents. At relatively low current density, I obtain a magnetization precession around the anisotropy axis with a very small precession angle. This angle increases when I increase the current, and eventually for large currents, I obtain almost a complete precession in the plane. When the current exceeds this threshold, the precession doesn't happen around the anisotropy axis anymore, but in the plane, around the demagnetizing field itself. You see that I have two regimes of auto oscillations. At small currents, the magnetization oscillates around the easy axis, and in this case, the larger the current, the larger the cone angle, and therefore the smaller the frequency. At larger current, the magnetization precesses in the plane around the demagnetizing field, and the larger the current, the larger the frequency. This relation between oscillation frequency and current has been uncovered by Kiselev experimentally. Here they measure the frequency as a function of the current, and you clearly see two regions, one where the frequency decreases when the current is increased, and the other where the frequency increases with the current. The tunability of the oscillation frequency with the current is a very important feature of spin torque oscillators. Another way to describe these excitations was proposed by Slavin and Tiberkevich. The idea is to start from the LG equation and look at the oscillating part of the magnetization. I can combine these two equations into a single one, where m plus is the variable I'll be tracking. Replacing m plus by the parameter c, I obtain this nonlinear master equation where I recognize the magnetic energy, enhanced by nonlinearities coming from the magnetic anisotropy. I also retrieve the magnetic damping, the linear spin torque, as well as a nonlinear spin torque term. What makes this equation particularly instructive is that all the key parameters appear in a transparent manner, and one can clearly see the role of nonlinearities. To solve this equation, I express the complex variable c in terms of its amplitude and its phase, which gives me two equations. Let me focus on the master equation of the amplitude r. By introducing this normalized parameter zeta, which represents the ratio between the torque and the damping, I obtain a nonlinear equation that is only governed by zeta. If the ratio between the torque and the damping is smaller than 1, the damping wins, and the only stable solution is R equals 0, meaning no oscillations. On the contrary, if the ratio is larger than 1, then the torque wins, and a non-zero stable solution exists, which means that auto oscillations are allowed. By pushing the theory further, one can obtain the relation between the oscillation frequency and the current, as observed experimentally. The two theories we have seen assume that the microspin approximation applies, which is far from true in many experiments. This is the case, for instance, in a nanocontact, where the torque is concentrated over a small region of the ferromagnet. In this case, the dispersive nature of the spin waves, the fact that their excitations can propagate, is going to be compensated by the nonlinearities coming from the anisotropy and the torque. As a result, the excitation state is rather represented by what is called a nonlinear spin wave bullet. If I inject the current from the nanocontact into the ferromagnet, I expect the magnetic excitations to adopt the oscillatory pattern given on the left. In fact, due to the nonlinearities and magnetic damping, I rather have the pattern on the right, that is, a much more localized excitation. This nonlinear spin wave bullet possesses characteristic current frequency relations that has been observed experimentally a decade ago. When the free layer has perpendicular magnetic anisotropy, a similar effect arises that has been called a spin wave droplet. Again, this droplet has specific current frequency response and features original, self-localized oscillatory states such as this one, or this one. Exciting one oscillator is fine, but coupling many of them is even more fun. This is something that Huygens realized a long time ago. He hung two pendulum clocks on the same wall and realized that they tend to synchronize. One can do the same with spin torque oscillators, as demonstrated by two groups from NIST, Hitachi, and Freescale. They use nanocontacts connected to the same extended free layers. Each nanocontact constitutes a single spin torque oscillator that couples through the spin waves of the free layer. The experimental results are shown here, where you have the power spectrum of the system as a function of the current injected in the spin torque oscillator B, while maintaining the current injected in the spin torque oscillator A constant. You see that the frequency of the oscillator A is weakly affected, whereas the frequency of the oscillator B increases strongly with the current as expected. In the region where the two dispersion curves cross, the oscillator A and B couple with each other and synchronize, resulting in a sharp enhancement of the output power at this frequency, as well as a very strong narrowing of the bandwidth. The two figures below give the spectrum of the system before and after synchronization. Spin torque oscillators have been realized in many different types of configurations. One interesting example is to use current-driven vortex oscillations, as done by the CNRS-Teles group. In this configuration, the oscillating state is a magnetic vortex whose core oscillates at gigahertz frequency when excited by a spin current. One can combine several of these vortices using nanocontacts, which gives this characteristic spectrum where you see the four individual eigenfrequencies. Under synchronization, one can substantially increase the power output while reducing the bandwidth, as discussed in the previous slide. Finally, another way to synchronize multiple spin torque oscillators is to take advantage of the spin torque from the spin Hall effect. In this case, the current is injected in the plane, which allows for exciting the oscillators in series. In this diagram, you can see up to 5 oscillators that get synchronized under appropriate conditions. The discovery of spin transfer torque has led Spintronics into a new era of innovation, One of the most promising inventions is the magnetic random access memory. It was originally introduced by IBM in 1955 with the so-called magnetic core memory concept, which remained the workhorse of magnetic memories until 1975 or so. This memory consists of an array of magnetic cores in which the information is stored. From magnetostatics, we know that the magnetization can adopt two equivalent configurations, curling either clockwise or counterclockwise. This state can be written by injecting a current in two orthogonal wires. The resulting electric field can switch the magnetic state of the core. This state can in turn be detected by induction using the sense lines. With the advent of the spin valve, the magnetic core memory concept has been upgraded to the field-driven magnetic random access memory. Now the magnetic state is stored in the free layer of the spin valve. To write the state of the free layer, you inject a current into the top and bottom wires, which generates an electric field. To read the magnetic state, you inject a current from the top to the bottom wire and measure the magnetoresistance. This approach has been the object of a lot of effort in the 1990s and early 2000s, but it suffers from a severe lack of scaling. As shown in this figure, the smaller the junction area, the larger the current you need to generate the electric field. Indeed, the electric field is proportional to the current, not to the current density, so it doesn't scale. The paradigm shift came with the spin transfer torque that scales with the current density. Here, you have a standard spin torque magnetic random access memory bit. This bit consists of a CMOS transistor on top of which lies a magnetic-to-NAND junction. This technology can be scaled down to very small bit sizes, typically 10 nanometers or so. This is currently the most mature Spintronics technology. A lot of effort is being paid to develop optimal stacks with enhanced thermal stability and reduced critical switching current. This is still a very active area and big tech companies are working hard to bring it to the market. So I encourage you to check out the latest news on these websites. Beyond magnetic random access memories, spin transfer torque is also a key enabler for several technologies including stochastic memories, microwave oscillators and detectors, as well as memristors and neuromorphic computing. If you're interested in learning more about these areas, have a look at this paper from the CNRS Thales group.
In this part, we have learned about the stability phase diagram of a ferromagnet submitted to spin transfer torque, and we have seen how temperature affects it. We have also talked about how to excite spin waves and a variety of self-sustained oscillations like spin wave droplets or spin wave bullets. And what is truly remarkable is the great flexibility that spin transfer torque offers for the design of a wealth of potential devices, from non-volatile memories to gigahertz oscillators and neuromorphic systems. In the next part, we are going to address the dynamics of magnetic textures, including domains, vortices, and skyrmions. So let's go for it.